Hi everyone, it's the 7th of January. My name's Gaz Roberts and this is the Black Knight project where we build carbon fibre rockets, use as many tools and technology as possible, and if we haven't got the tools, we're going to make them. Now at the end of the last video we came across a problem, or I came across a problem. Now we've got the motors in, we've got our stability, and we've got all basically the main elements designed of the rocket. Now what I came across and what I was worried about is something called the delay. Now what happens with a model rocket, when you light the engine, the rocket whoosh, off it goes. Now the motors say burn for 2 to 3 seconds on these smaller motors. Now once the motor is burnt out, the rocket just doesn't stop. It's got so much energy, it wants to continue on up until the point where the air friction and the drag from the air slows the rocket down to the point where it completely stops, wants to turn around and come back down like a ballistic missile. Now what you do to stop it coming down like a ballistic missile is you have what's called an ejection charge. Now this injection charge is basically at the end of the motor. There's some black powder that turns your rocket into a cannon. It blasts the nose cone off, which then pulls out a parachute and, or in this case a streamer, and it all comes flying back down to Earth. Now this is meant to happen at the very highest point of the rocket, where the rocket in theory is not relatively doing any speed at all, so it's at the top just before it starts to drop. Now what you do is you calculate where the apogee is going to be. So what we're going to do, we'll do that now. So we're going to pick the B motor on the right hand side. So we'll pick the B motor. We'll go to flight simulations. Now there's no simulations run here at the moment. We know our stability is okay, that's not a problem at all. So we're going to run a simulation. Now there's plenty of settings in there. You've got average wind speed, we've got turbulence, we can put where we are, so we can try and get stuff like the altitude. But at the moment we're just going to leave pretty much the standard settings in it. You've got how long your launch rail is, but we're just going to OK that for now. So we'll OK simulation 1. It runs a little simulation. Now what we've got here along this top row is we have got the motor configuration, we've got the speed that it comes off the rail, which we'll talk about in a second. We've got the apogee. Now this is quite clearly beating the record at the moment. We have got 344 meters, and to take the record we only need 253. So it's a margin that we've got there. But the problem that we've got again is the delay. Now the delay, optimum delay, if we have a look, which means when the rocket is at the very top of the curve, we want to pop the parachute, or in this case a streamer, out, is almost 7 seconds. But the B motors, if you have a look at the end of the motor, the last digit there, the number 4, represents how many seconds after the motor finishes burning out that the motor fires the black powder, which will eject the parachute. So it's going to come out at 4 seconds. So it's coming out a full 3 seconds before the rocket gets at the top. So this rocket's still going to be moving. So what we need to do is check literally how fast it's going to be moving and if the rocket will survive. So we're going to plot a graph. So if we plot a graph now, we'll leave all the settings standard again, click plot. Now this brings up a simulated graph. Now if we have a look at the blue, this is in meters, so we can basically see we're hitting our 350 nearly, which is our 344. So that is at the very top. Now if we have a look at the seconds along the bottom, and we know that our apogee is almost 8 seconds, 7-8 seconds, which is perfect. But then if we trace back down to acceleration, the vertical acceleration, and we know that the injection charge is going to come out at 4, the rocket is still accelerating up, so up and up and up. So we're around here on the curve. So if we go back down, it's coming out at 44 meters a second. Now, off the top of my head, meters per second converted to mile an hour is about 2.5 mile an hour per meters per second. So it's going about 90, 100 mile an hour. So the other problem that we need to look at, if we can get the rocket to survive the injection, how high is it actually going? So we trace our line up from 4 seconds and we go up to the 4-second mark, 4 seconds and a couple of tenths, so that's close enough. We are at 277. Now, in theory, the rocket may tumble and continue up slightly, so we may get a little bit more, or it could tear itself to pieces. So if we just go back and we've got 277, yeah, so we're beating the record by 100 and odd feet, or close to. So in theory, I am happy enough with that. So the main problem that we're going to have is how to get the rocket to survive. But to build the rocket, design the rocket, we're going to have to use something sufficiently strong enough, something Kevlar would be. We can get thin diameter Kevlar that's extremely strong, and we'll probably go around, I don't know, maybe 100 foot-pound of strength. So we'll try that anyway, but in the video of the build video, when we're working it out and we're using what products, we'll do a little video on how we worked out exactly what kind of strain is going to be on our shock cord. So we're just going to have a look at a few of the other motors now. So obviously this one is going to be extremely shocking. It's going to put a lot of strain on it. Now this is maximum strain. It could be tumbling, it might slow down before the cord actually snaps. So now we're going to go back over and have a look at the other motors, so we can just close everything down. Well, now we'll have a look at the C. Now the longest delay that you can get in this C motor, if you have a look at the end here, is a 7-second delay. So I'm a bit more optimistic that this is going to be closer to apogee. Obviously the motor's twice as powerful, so we've got to take that into consideration, but the delay is almost twice as long. So we'll run a simulation on the top, new simulation. Again, default settings, okay. Now we'll review our lines again. It's coming off the rail faster, which is never a bad thing because it'll help all the aerodynamics and the stabilization kick in faster. Apogee, it's getting a hell of a lot higher, so we'll have a look at our apogee at the moment against the record. So we could get it right to the very top, where we need to beat 458, so this time we're significantly beating it. And our optimum delay is 8.2. Now there's not a huge difference because the maximum acceleration is always deaccelerating the most, so between 7 and 8 seconds. I'm quite optimistic that when we run and plot our graphs, again default settings, so if we have a look at 7 seconds, so 7 seconds 615, so we're clearly beating the record even at 7-second delay. And again we need to have a look at the speed. So we have a look at the speed, it's massively reduced on the curve, and at 7 seconds we are down to 27 meters, 26, rapidly descending down to meters per second. So we're coming into very survivable and a lot less strain on the rocket and the shock cord itself. So I'm thinking we're looking extremely good with that one, to be fair. Now we'll also finally having a look at the D. Now again, the D comes with a 7-second delay with the number on the end, but we're twice as powerful again. The delay is not twice as powerful, so we're going back to the same kind of power to rate ratio and early delay as the B motor. So I'm guessing we're probably going to get the similar kind of strain on the shock cord 3 meters per second at deployment. So let's have a look. So again, standard settings. So again, we're coming off the rail faster, so we're going to get our active aerodynamics and stability quicker, which is always good. Apogee, a phenomenal, that's nearly 3,000 feet. So let's have a look. Again, we're 25% over the record. In theory, now an optimum delay is 9 seconds, so in theory, maybe not too bad. But if you have a look at the max speed that it's hitting, we're hitting 276 meters per second. So this thing is motoring. Maximum acceleration, again, massively metered squared. Time to apogee, not that much difference, but it's getting there quick. Ground velocity is going to be exactly the same because the burnt out rocket is very similar weight in motor, and that's what the stream has given us. I'm more than happy a carbon fibre rocket should be taking that kind of impact into the ground. Now we'll run our plot and simulation again. Now looking at this, we know we're on a 7-second delay, so we work out to about 7 seconds, and yes, we'll be beating the record. And what kind of speed are we doing? Even though it's rapidly de-accelerating at 7 seconds, we're doing roughly as suspected, the same kind of velocity. So again, this is going to put a lot of shock onto the shock cord. So when we're actually building, testing this rocket, seeing how much shock cord and how much streamer we can get in, which is going to massively affect and take some of the strain off the shock cord. We'll do some maths and calculations. We're going to have to build the rest of the design around survivability on the B motor and on the D. So we'll see where we can get from there. So now I think the next video, part 3, we'll go on to designing and doing a mock 3D design. So we're going to basically build a full-scale model, fully 3D printed, and I'll show you how you can get from this to a fully 3D printed prototype model in about 5 minutes of your time, and then anything between half an hour and a couple of hours print, depending on what printers you've got. So please join me next time. Things are going to get a lot more exciting. We're going to have to build some tooling. We'll actually start building the mould, and we'll actually start firing some engines, and we'll see some smoke, some fire, and hopefully no explosions. Thank you.